Similar to a mirror, a lens can be, or the image position of a lens can be determined using a ray diagram. First we draw a ray parallel to the axis through the focus. Next we can draw a ray that passes through the center of the lens and it will continue straight on. Alternatively, we can draw a ray that passes through the focal point prior to the lens and it will emerge parallel to the axis. If we draw all or two or more of these rays, we can determine where the image is formed by finding the intersection of the rays. Note that we've only determined the top of the image here, and we know that the bottom of the image lies on the axis, in this case the blue line. Similar to a convex lens, we can use a ray diagram to determine the image position and properties of a concave lens. So first, just like in the previous example, we draw a ray parallel to the axis, and it in this case emerges as if it had come from the focal point before the lens. Then we can, just like in the convex lens, draw a ray that travels through the center of the lens and it continues straight on. We could use a third ray, but for the concave lens it's quite complicated, so in this case we'll just use the two, and again we can determine the top of the image by finding the intersection. When we look at the magnification of an object using a convex lens, we see that if the object is quite close to the lens within the focal distance, then there is some magnification of the object at a point fairly close by, and we can see that where the intersection of the rays occurs. As we move the object further away from the lens, getting closer to the focal point, the image appears larger and larger and progressively further away. As the object reaches the focal point, the rays are now parallel, which means we cannot have an intersection and therefore no image is possible. Once the object moves beyond the focal point, we no longer have an intersection behind the lens. The intersection is now in front of the lens, and if we were to extend those lines, we would see the intersection there, and that means that we now have an image in front of the lens and it is also inverted, so upside down. So just like with mirrors, we can determine image properties numerically instead of using a ray diagram for a bit more accuracy. So here we have an example of a ray diagram for a concave lens, and we're going to just determine the image properties numerically. So in this example, the object of a man is positioned at 9 centimeters from the lens, and the focal point of the concave lens is 3 centimeters. So we have to use the same equation that we had for mirrors. If I do, I die, we can use to remember. The reciprocal of the focal length is equal to the reciprocal of the object distance plus the reciprocal of the image distance. We can rearrange that and then put our values in, and we have to make sure that we remember that the focal point of a concave lens is negative. So when we put those values in, we end up with a result of minus 2.25 centimeters, and we can see that that matches where the man is positioned on the ray diagram. He's 2.25 squares away from the lens. We also need to determine the height of the image, and we can use the mnemonic hi ho, di do, it's off to magnify we go. So that's magnification factor equals image height divided by object height, and it also happens to equal image distance divided by object distance. So if we put the values that we have for the image distance and the object distance into that equation, we end up with a magnification factor of 0.25, and as we can see, the man is 4 centimeters high, multiplied by a magnification of 0.25. That comes out with an image height of 1 centimeter, which again matches that seen on our ray diagram. So we have the image distance 2.25 centimeters before the lens, and the height is 1 centimeter.